When I was younger, I labored under the misconception that in order for mathematics to be beautiful, it had to be complicated. But as I got older, I got a little wiser and began to realize that even simple objects like equilateral triangles possess great mathematical beauty. And I want to try to convince you of that today. So let's start by trying to put the equilateral triangle into its proper historical context. Indisputably, the most influential mathematics book ever written was Euclid's Elements, written about 300 BC in Alexandria. And what is in Book 1, Proposition 1 of Euclid's Elements, other than the construction of an equilateral triangle given one of its sides? Now, the version of Euclid that I have here is in Greek. It is the oldest extant, complete copy of Euclid's Elements. It now resides at the Bodleian Library at Oxford and was transcribed by Stephen McCartin from Constantinople in 1482. But that certainly was not the first appearance of the equilateral triangle. For example, there are the remains of a human settlement on the banks of the Danube River in modern-day Serbia called Lipinski Vir. And the houses themselves are gone, but the bases of the houses are still there, and they are all built on an equilateral triangular floor plan. So they're not built in the shape of a rectangle. They're not built in the shape of a circle. They're all built in the shape of an equilateral triangle. And this is 3,000 years before the pyramids were built. Now, speaking of the pyramids, there's one in particular that I'd like to call your attention, and that is Snefru's bent pyramid. The Egyptians started the pyramid at a 60-degree angle, so that if they had been successful in completing it, the cross-section of the pyramid would have been an equilateral triangle. As soon as they started to build it, it started to fall apart. And so they went back out further and came in at 54 degrees. Now, 54 degrees would have given equilateral triangular faces. But when they got halfway up, it began to collapse again. And so they tilted it at 43 degrees, about halfway up. So it goes from 54 to 43. So each face of the pyramid is bent. But it seems that the Egyptians were hell-bent on getting equilateral triangles incorporated into this building. If we move to Babylonia, we still have some clay tablets from Babylonia, and one of them, so-called BM 15285, BM the British Museum where it now resides, is a textbook. And one of the pages of the textbook right here concerns itself with an approximate construction of an equilateral triangle. And if we move to the sister civilization of Babylonia, Assyria, we find that their altars were typically of an equilateral triangular base. So we see many equilateral triangles in antiquity. If we move to India at Chennai, on one of the stone pillars at the temple at Chennai, there are 3 interlocking equilateral triangles shown here. And they're locked in what's known as a Brunnian link. A Brunnian link is such that if you were to cut one of the equilateral triangles and remove it, the other 2 triangles would also separate. In other words, the 3 triangles are interlocked, but no 2 of them are interlocked. It's quite strange. And that's portrayed in Chennai, in India. If we move to China, the 3 pagodas of Changsheng Monastery all stand at the vertices of an absolutely precise equilateral triangle. And this is the only such configuration in China. Now, in the 6th century BC, the ancient Greeks were quite enamored with the number 10. They worshiped the number 10, the so-called decad. And they typically would display it like this, with 10 dots arranged in an equilateral triangular pattern. And they named it the tetractys. In other religions borrowed it from the Pythagoreans. For instance, we have the Hebrew tetragrammaton, which has the same pattern. And even the Catholic archbishops' coats of arms incorporate the tetragrammaton. The tetractys, rather. And in modern tarot card arrangements, sometimes they also use the tetractys. Now, the Greeks were also enamored of the so-called Platonic solids. They're called the Platonic solids because Plato introduced them in the Timaeus. But in fact, It was Euclid who proved that there were only 5 of them. The constraint being that each face has to be a regular polygon, all faces have to be congruent, and all vertices have to be identical. There are only 5 such Platonic solids. 3 of them are composed of equilateral triangles: the tetrahedron, the octahedron, and the icosahedron. So 3 out of 5, that's not bad. Now, if we relax the constraint that the faces have to be congruent and allow different polygons on different faces, we get the so-called Archimedean solids. And there are 13 of them. That was proved by Kepler. And of the 13, 9 of them have equilateral triangular components to them. So 9 out of 13. And that brings us to deltahedra. A deltahedron is a convex polyhedron whose faces are congruent equilateral non-coplanar equilateral triangles. That's a mouthful. But basically, all the faces have to be equilateral triangles. And if you insist that they be convex, in 1947, Freudenthal and van der Waals proved that there are only 8 of them. They have 4, 6, 8, 10, 12, 14, 16, and 20 sides, respectively. So mysteriously, 18 is missing. And it can't be done, that was proven, but people have tried nonetheless. And they've come close. In 1978, Frost and McGovern presented the deceptahedron, which is almost convex and composed of equilateral triangles. So this is as close as we've come. Now, in Christian art, the equilateral triangle is usually reserved for the body of Christ. Here's Da Vinci's Last Supper. Christ is an exact equilateral triangle. As it is in Pontormo's Supper at Emmaus, but also now we have an equilateral triangle above the head of Jesus enclosing the eye of God, the triangle symbolizing the Holy Trinity. And my favorite is the 1951 painting by Salvatore Dali, Christ of St. John of the Cross. And this came to him in a dream, okay, to portray Christ as an equilateral triangle, to view it as God the Father would see the crucifixion, and project Christ onto an equilateral triangle. So we see it throughout Christian art. And even in the 20th century, right, Church of Scientology uses equilateral triangles in their icons. Moving to music, if we take the so-called circle of fifths from music theory and inscribe an equilateral triangle, we get a chord called an augmented triad. And this is a very important chord in classical music and very popular in jazz. In terms of architecture, the Gateway Arch in St. Louis, of course it's an upside-down hyperbolic cosine, but the cross sections, if you were to slice this with a plane, each cross section is an equilateral triangle. Now, my favorite show from the 1960s, the original Star Trek, had an episode called The Gamesters of Triskelion. And Triskelion was a planet that was in a ternary star system. Kirk and crew had to fight for their lives on an equilateral triangular battlefield for the amusement of the providers, who were disembodied brains residing at the vertices of an equilateral triangle. Get more equilateral triangles. Now, more apropos for your generation, we've got Harry Potter and the Deathly Hallows, where the equilateral triangle represents the cloak of invisibility, the in-circle, the resurrection stone, and the altitude, the elder wand. So again, we see equilateral triangles throughout human culture. And that brings us to the mathematical properties of the equilateral triangle. And I'd like to begin back with Euclid again. Constructing an equilateral triangle from the side. The way that Euclid does it, you get your compass and you put the point here and the pencil there, draw a circle. Then reverse the roles of the 2 points, draw another circle. Where they intersect, those 3 points form an equilateral triangle. So that's the proof in Euclid. Now, if instead of being given a side, suppose instead we're given a circle and asked to inscribe an equilateral triangle, then there are at least 2 ways that are known to do that. The first is due to Hopkins. So you're given the center and the radius of a circle. So you put the compass point anywhere on the circumference, and you draw this portion of a circle and tick off D and E. Then put your compass point at D and E, and tick off A and B, and you've got your equilateral triangle A, B, and C. You can prove that that works. Or Eric Weisstein has constructed it as follows. You draw a diameter, then you bisect the diameter, you bisect it again, and where that second bisector intersects the circle, together with this third point on the diameter, forms an equilateral triangle. Now what's truly amazing is that Euclid's construction can be generalized to a so-called rusty compass. A rusty compass is exactly what its name implies. It's a compass that's rusted into position, and you can no longer open and close it. You have to draw circles all of one size. You can't adjust the opening. And you can start off like in Euclid. You take AB, center at A, draw a circle. Center at B, draw a circle. They intersect at D. Use that as the center of a third circle. That third circle intersects the original two at E and F. Use those as centers. They intersect at C, the third vertex of an equilateral. You can prove that. And the amazing thing is that this appears in a book called Circles by Dan Bedell. And he attributes it to a student that he caught doodling in his class. The student was doodling, and he picked up the paper, and this is what was awaiting him, an original rusty compass construction. So students daydreaming in class is not always bad. Usually it's actually not always bad. Now, one of the simplest theorems about equilateral triangles is Viviani's theorem. Viviani's theorem says if you take an equilateral triangle, pick a point inside, and then add up the sum of the three distances to the sides, it's always equal to the height of the triangle. And because of Viviani's theorem, you can go into an equilateral triangle and take three quantities, A, B, and C, and construct what are known as trilinear coordinates. You assign each variable to a vertex, and let's focus on A. We go to the opposite side. Lines parallel to that will measure how much A you have. So for example, this is 0% A, 10% A, 80% A, 90% A, 100% A. And you can do that for the other two vertices. So now you can actually graph relationships between three variables on such a triangle. And those are called ternary diagrams, and they're very common in science, and I'm going to show you an example later in the talk when we talk about applications. Now, another beautiful theorem about equilateral triangles is Morley's theorem. Morley's theorem says, take an arbitrary triangle, it is not equilateral, and trisect each angle, cut them in three, and wherever adjacent trisectors meet, those points form a triangle, and a triangle is always equilateral. That's called the inner Morley triangle. If you do the same thing for the exterior angles of the triangle, you get the outer Morley triangle. Sorry, the first and the second Morley triangle. A companion result is due to Napoleon, right? The famous military guy, Napoleon. He has his own math theorem. And it says the following. Start again with an arbitrary triangle, it's not equilateral, and on each side erect an equilateral triangle. Connect the centers of those three equilateral triangles, and you get a fourth equilateral triangle, the inner Napoleon triangle. Sorry, the outer. And if you make these equilateral triangles point inwards rather than outwards, you get another equilateral triangle. So it's not difficult to produce equilateral triangles from an arbitrary triangle. Now, a little mini review of some high school geometry. Three terms. The orthocenter is the intersection of the three altitudes of a triangle. The centroid is the intersection of the medians. And the circumcenter is the intersection of the perpendicular bisectors. Those 3 points in an equilateral triangle coincide. But for an arbitrary triangle, there are 3 different points, but they always lie on a straight line. And that line is called the Euler Line, and it's a very famous result. What's not so widely known is if the original triangle has a 60-degree angle in it, then the Euler line always slices off an equilateral triangle. So there's another, and that result is only less than 10 years old. So you might think that everything is known about triangles that could be known. That's wrong. People are to this day discovering things about triangles. Now, in 1775, Giulio Fagnano posed the following problem. You're given an acute triangle, and you have to inscribe a second triangle inside that triangle, and you have to make it as small as possible. His son solved the problem, his son Giovanni, and he proved that the solution is the pedal triangle, formed from the feet of the three perpendiculars, the three altitudes. So these are the feet of the three altitudes. That's called the pedal triangle. Now what does that have to do with equilateral triangles? Well, let's call this the pedal mapping, where you start with the original triangle and then you map it to its pedal triangle. Then the equilateral triangle is the unique fixed point of that mapping. What does that mean? It's the only triangle that doesn't change shape. Notice here, when you form the pedal triangle, it changed shape from the original triangle. Here it does not. And it's the only such triangle. All other triangles change their shape. So equilateral triangles like to stay equilateral. Now I'm sure you've all seen fractals, and there are a couple of very famous fractals associated with the equilateral triangle. For example, the Koch snowflake starts with an equilateral triangle and adds more and more equilateral triangles. As opposed to the Sierpinski gasket, where you start with an equilateral triangle and you subtract more and more equilateral triangles. So those are famous. Here's a new one, less than 10 years old, due to Hans Waldsen, the golden triangle fractal. The golden number is 1 plus square root of 5 over 2. It's a very famous math number. And you can use it to build a fractal as follows. Start with an equilateral triangle, and then attach to it 3 other equilateral triangles. How? So that the length AB divided by BC is in the golden ratio. So that that ratio is 1 plus square root of 5 over 2, about 1.61. And then repeatedly do that. Add on more triangles and more triangles. Surprisingly, these branches do not overlap. They come close to touching, but they never touch. And you get this beautiful tree structure in the limit as you do it infinitely many times. So there's the golden triangle fractal, a new kid on the block. Now I'm going to assume, I'm not going to assume much today, but I'm going to assume you know what Pascal's triangle is. Pascal's triangle, if you take the odd numbered entries in Pascal's triangle and paint them red, and take the even numbered ones and paint them black, and then shrink, of course Pascal's triangle is infinitely long, it's infinitely big, shrink it down to a finite size, and you will get none other than the Sierpinski gasket that we saw on the previous slide. So in other words, inside Pascal's triangle is hiding a fractal associated with the equilateral triangle, the Sierpinski gasket. And as we'll see, this guy pops up a lot, Sierpinski gasket. For example, in the chaos game, how do you play the chaos game? Well, you start with an equilateral triangle, and you number the vertices, and then you pick a point at random in the triangle. And then you take a die, a single die, 1 through 6, and you roll it. And if you get a 1 or a 6, you move towards this vertex. If you get a 2 or a 5, you move towards this vertex. And if you get a 3 or a 4, you move towards that vertex. So suppose we roll a 6. So we're going to move towards this vertex. We're always going to take half the distance. And then repeat the process. Roll the die again. Suppose it comes up 2. So you're going to move towards this vertex, but you're always going to take half the distance. And you do that 100, 500, 1,000, 10,000, infinitely many times. And guess what you get? It approaches the Sierpinski gasket. So the Sierpinski gasket is a very persistent fellow. Now the Fibonacci numbers, you start with 1, 1, and then you add 1, 1, 2, 3. You always add the previous 2 entries. 5 from equilateral triangles. And the way you do it is as follows. You tile the plane with equilateral triangles. And then you start with a triangle, a rhombus, and a trapezoid. And then thereafter, you always put a trapezoid under a rhombus and a rhombus under a trapezoid. So, trapezoid under rhombus, rhombus under trapezoid, and so on. And look at the sides of the rhombi. 1, 1, 2, 3, 5, 8, 13, and so on. So it immediately generates the Fibonacci sequence. This was just discovered in 2009 by Hans Walzer, the inventor of the golden triangle firm. Now, if you take the ratio of successive Fibonacci numbers, 5/3, 8/5, 13/8, it approaches the golden mean, 1 plus square root of 5/2. You can construct it directly as follows. Take and inscribe an equilateral triangle in a circle. We already saw 2 ways to do that previously. Then pick the midpoints of 2 sides and connect it with a line segment and intersect the line until it hits the circle. Then the ratio of LM to MY you can prove is in the golden mean. Now the amazing thing is that this was not done by a mathematician. This was done by an inmate of the Hudson River Psychiatric Center in New York State. He mailed it to a math professor who got it published. So the moral of the story is, you don't have to be crazy to do math, but it sure helps. Here's a beautiful result due to Conway and Guy. Suppose you want a triangle, and suppose you want its angles and its sides to be rational numbers, fractions. There's only one such triangle, equilateral triangle. There is no other triangle. If a triangle has rational numbers, if the lengths are rational and the angles are rationals, it is an equilateral triangle. And here's another simple result. No equilateral triangles on a chessboard. What does that mean? Well, here's an infinite chessboard. You have to connect the corners of the squares, pick any 3 of them, and try to connect them so that they form an equilateral triangle. So for instance, there's a triangle right there. That's not an equilateral triangle, because I know it's impossible. And the way I found out about this result is the journal Mathematical Intelligence in 1990 polled all its readers, and they gave us 24 choices and asked us to vote for the most beautiful theorem in the world. And this came in at number 19. This is number 19 on the charts. You see the equilateral triangle. And my last theoretical result requires a definition. Similarity transformation means a function that preserves shape. So the function is allowed to rotate an object, reflect an object, translate an object. It can shrink it, it can magnify it, but it cannot change its shape. That's the definition of a similarity transformation. And of course, a similarity transformation has to preserve equilateral triangles, has to preserve everything. But in 2004, Sikorsky and Zostak proved the converse. And that is, if any function preserves equilateral triangles, doesn't change the shape, then it doesn't change the shape of anything. Why is that so remarkable? Well, it says that equilateral triangles are like the atoms of shape. Right? If you want to prove that something preserves shape, just check out the equilateral triangles. If it does that, it preserves all shapes, no matter how complicated. So that's a surprising result. Applications. Right? This is Kettering. Right? We're interested in how mathematics applies to the world around us. Let me show you some examples. And I'll begin with a couple of simple examples. In surveying, there is the equilateral triangle method. So you're out in the field surveying, and you run into either a large building or a hill, and so you cannot survey through it. So you can survey around it. You swing around at 120 degrees, you go a fixed distance, then you swing 60 degrees, go the same distance, and then swing 120 degrees. Then this is guaranteed to be an equilateral triangle. So that means you now know what this distance is and you can complete the survey. So there's a simple application of the equilateral triangle for surveying. Here's another one that you might not know about, but you should know about. And that is setting up your stereo speakers in your dorm room. You're supposed to arrange them so that your head and the equilateral and the speakers form an equilateral triangle. The reason for this is the way that most stereo recordings are made. The band is located at one vertex, and then 2 identical microphones are placed at the other 2 vertices of an equilateral triangle. And by the so-called reciprocity principle of acoustics, if you want to reconstruct that, you want to simply interchange transmitter with receiver. You want to listen to it in an equilateral triangle configuration. So if you want to get the maximum stereo reconstruction, you want to listen at the 3rd vertex of the equilateral triangle. Now, my third application is a little more complicated. Our hearts, our human hearts, are electric dipoles. And so electric dipoles, as you know from physics, have an axis. That axis runs from the right shoulder towards the left leg. And if your heart is at an angle significantly away from that, then your heart valves will be under stress. It's called ventricular hypertrophy. And doctors detect this problem as follows. They put an electrode here, and an electrode on your leg in an equilateral triangle shape. And then they measure the potential between those 3 points. So now you know the potential difference on the 3 sides of this Einthoven triangle, and you can reconstruct the cardiac vector, because it's the projection of the cardiac vector onto the sides. So from the 3 projections, you can reconstruct the vector. And that's called the principle of the equilateral triangle of electrocardiography. So that one's a little more substantial. Now, much of applied mathematics has grown out of a single problem in celestial mechanics. It's called the 3-body problem. You've got 3 objects all interacting gravitationally, and you want to track out their paths. Turns out that there are only a few scenarios where we know the exact solutions to those equations. And one such is Lagrange's equilateral triangular solution, where each body moves around an ellipse. Each ellipse has the same eccentricity. They share a common focus, which is the center of mass of the system, and the 3 objects are always at the vertices of an equilateral triangle. But as they spin around, the triangle grows, and then shrinks, and then grows, and then shrinks. But as it grows and shrinks, it's always equilateral. Now, the problem with this solution is that in order to see it in practice, you have to have very, very special initial conditions. And so nobody's ever observed this in nature. People have derived it mathematically. Unlike the following configuration, also due to Lagrange, the so-called circular restricted 3-body problem. Here, you have a really big body, a medium-sized body, and an itsy-bitsy tiny body, and they're all spinning around each other. Well, there are 5 equilibrium positions of those 3 bodies, only 2 of which are stable, and both form equilateral triangles. This we do see. We see it a lot in our own solar system. For example, the Sun, Jupiter, and the so-called Trojan asteroids sit at the vertices of such an equilateral triangle. And there are many other examples. I've listed a couple of more. Okay, pop quiz. What's the largest scientific instrument in the world? The Large Hadron Collider outside of Geneva. It's got a circumference of 17 miles. It's a particle accelerator. It's going to lose that title in 2020 when European Space Agency and NASA launch a trio of probes that's going to try to confirm the last undetected prediction of Einstein's general theory of relativity, and that is the presence of gravitational waves. Einstein predicted them. No one's ever been able to detect them because they're so weak. So they're going to launch a trio of satellites. It's going to follow the Earth about 20 degrees behind in its orbit around the Sun, and they're going to be in an equilateral triangular configuration 3.1 million miles on an inch. And that is likely to hold the title as largest scientific instrument for quite some time. There's that pesky Sierpinski gasket again. Physicists and electrical engineers have constructed superconducting Sierpinski gaskets. Now, of course, Sierpinski gaskets are infinitely long, so you can't do it infinitely many times, but they've gone down 10 levels of refinement. And when you go down that fine, the side of the smallest equilateral triangle is about 2 microns. How small is 2 microns? Well, a human hair is approximately 100 microns. So these are tiny Sierpinski gaskets. I did promise you a ternary diagram when we talked about Viviani's theorem. I've got 4 of them here. I'm only going to show you one. This one right here. Maxwell's color triangle. This is to say Maxwell that discovered electromagnetic waves. He was also into color vision. And this Maxwell color triangle is used in computer graphics. Because on your computer screen, no matter how exotic the colors are, they're all formed by mixing red, green, and blue. And the way you determine how to mix red, green, and blue to get a particular color is you put red, green, and blue at the vertices of an equilateral triangle, set up a trilinear coordinate system using Viviani's theorem, and then, for instance, if we want yellow here, we just take the trilinear coordinates of that point and it tells us how much red, how much green, and how much blue. So these are very useful entities, these ternary diagrams. Now, we don't have a map in this room. We've got a periodic table. If you had a map, it almost undoubtedly would be a so-called Mercator projection. And that's a projection of a sphere onto a cylinder. And it notoriously distorts size. For example, on a Mercator projection, typically Greenland is the same size as South America, when in fact it is nowhere near the same size. Now, people have tried to correct that. One thing, in 1913, Cahill said, let's replace the cylinder, let's use one of those Platonic solids, the 8-sided octahedron. And let's project a sphere onto an octahedron and then fold out the 8 sides into this butterfly pattern. And notice now Greenland is much more realistic in size. And in 1943, Fisher went in one better. He said, well, an icosahedron looks a lot more like a sphere than an octahedron does. Let's use that. So you've got a 12-sided figure here. And in this case, it was patented by Fisher, the likelihood method. So there's another practical application. And the last application I'm going to show you is done tongue-in-cheek, no pun intended, computational confectionery. This was invented by a mathematician at MIT by the name of Eric Demain. And he studied the following problem. In Salzburg, they make a candy called Mozartkugel. Kugel is German for sphere. It's a little chocolate sphere with some filling. And it's called Mozartkugel because Salzburg is where he was born. And they make like 40 million of these a year. And it has to be wrapped up in foil. So they use a lot of foil. And the way they figure out the smallest piece of foil to use is they take the candy and mentally slice it into 4 petals and then inscribe a square around it. That's the smallest square that you could wrap the chocolate in. And then they wrap it up. Well, Demain said, why don't we replace this by an equilateral triangle? And he proved, after he did the integrals, he proved that you save 1/10 of 1%. Multiply that by 40 million per year. That's a lot. That's a lot. Now, people have been doing mathematics for a long, long time, thousands and thousands of years, and for various reasons. Many times practical reasons, but sometimes just for fun, to play games, to solve puzzles. And let me show you the equilateral triangle and some of those kinds of things. For example, there was a famous British puzzlist named Herbert Dewdney. He lived at the end of the 19th and beginning of the 20th century. And in 1905, he solved the so-called haberdasher puzzle. And the haberdasher puzzle is as follows. You have a triangular, equilateral triangular piece of cloth. You have to slice it into 4 pieces with straight line cuts, and then reassemble the 4 pieces in the shape of a square. Now the amazing thing is that mathematicians had proven that you needed 5 cuts. Okay? He showed that there was a problem with that proof, that it could be done with 4 cuts. And not only that, he showed how to do it as a hinged dissection. So here's the equilateral triangle cut into 4 pieces and hinged together. And the beautiful thing is, if you close the hinges in this direction, you get a square. If you close the hinges in this direction, you get a triangle. And he went one step further. He actually built a table like this, and he donated it to the Royal Society of London. Now think of how useful this would be in your dorm room. You got 3 buddies over and you're playing poker. One of them has to go home. Ready to go with 3. Now in 1964, Solomon Golem invented reptiles. A reptile is a polygonal shape that you can use to construct larger versions of itself. So for instance, this shape right here is called the Sphinx. It's called the Sphinx. And notice if you take 4 sphinxes, you create a bigger Sphinx. And it's called a reptile because you needed 4 of them. Now, what does that have to do with the equilateral triangle? Well, you can think of it as 6 equilateral triangles. 1, 2, 3, 4, 5, 6. There's a sphinx. So a sphinx, you can think of it either as 6 equilateral triangles pasted together, or 2/3 of an equilateral triangle. Because if you take an equilateral triangle, take its centroid, draw sides parallel to the edges, you get 3 trapezoids. Take 2 of those trapezoids and shade it in, you get yourself the sphinx. So you can either think of it as 6 equilateral triangles or 2/3 of an equilateral triangle, but equilateral triangle nonetheless. And here's the thing, this is the only known 5-sided rep 4 type. If you can discover another one, mathematical fame awaits you. Now actually Golem is more famous for something else. He invented polyominoes, which is the basis for the computer game Tetris. Those little shapes in Tetris, those are polyominoes. He invented them. The mathematical typesetting language LaTeX, it's written in a computer language called TeX, T-E-X, where X is a Greek chi. The inventor of TeX is Donald Knuth. He's a professor at Stanford University. But after he got his PhD, he started off at Caltech. And when he was 20 years old at Caltech, he analyzed the motions of pool balls on an equilateral triangular table. And of course, when the balls bounce off the sides of the pool table, angle of incidence has to be equal to angle of reflection. And the way he analyzed it was as follows. He said, well, reflect the table in itself and using a triangular lattice, and then straight lines on this lattice correspond to the pool ball paths. And so he was able to completely analyze the game using this idea. But he's not the first one to come up with the idea of using triangular lattices to analyze games. There's a much older example. It goes back to the 16th century. A fellow mathematician named Tartaglia published a book of puzzles, and one of the puzzles was the 3-jug problem. In the 3-jug problem, you've got 3 jugs. You've got an 8-ounce jug, you've got a 5-ounce jug, and you've got a 3-ounce jug, and the 8-ounce jug is full of water. And what you want to do is you want to pour 2 4-ounce servings. So you have to somehow pour 4 ounces from the 8-ounce jug into the 5-ounce jug. The problem is there are no markings on the jugs. There's no markings at all. So you either have to completely fill jugs or completely empty jugs until you get a 4 and 4 split. And in 1939, Tweedy showed how to solve this problem using an equilateral triangle. He said, use Viviani's theorem. Put the 8-ounce jug at this vertex, the 5-ounce jug at this vertex, the 3-ounce jug at this vertex, and then use trilinear coordinates. For example, 800 indicates the 8-ounce jug is full, the other 2 are empty. Here's where we want to get to, 440. 4 ounces in the 8-ounce jug, 4 ounces in the 5-ounce jug, and a 3-ounce jug empty. Here's how we do it. First of all, we have to stay on this parallelogram, because if you go out here, you have more than 5 ounces in the 5-ounce jug. If you go over here, you've got more than 3 ounces in the 3-ounce jug. So what you do is you take a pool ball, and you make believe this is a billiard table, and you simply roll the pool ball down. Now you have to make a decision at the beginning. You have the 8-ounce jug, it's full. You either have to completely fill up the 5-ounce jug or completely fill up the 3-ounce jug, one of the two. If you choose the 5-ounce jug, it's this picture. If you choose the 3-ounce jug, it's that picture. Let's analyze this picture. So we start off by filling the 5-ounce jug. Okay, that means we swing the pool ball down here until it hits 350. Angle of incidence equal angle of reflection. Bounce, 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 440, you're home. And every time you bounce, that corresponds to doing a pouring. So you just write them down and then do those moves, and you can solve the problem. Eternity puzzles. I know many of you are into puzzles. Here's a good one. It came out in 1999. A British mathematician by the name of Chris Monckton invented it. So here's a good entrepreneurial example. Okay? He invented this game called the Eternity Puzzle. It comes with a game board with 12 sides. It's got an equilateral triangular lattice printed on it. and you're given 209 differently shaped puzzle pieces, but they're all constructed out of 12 half equilateral triangles. So 30, 60, 90 triangles. So let's see here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? So there's 12 half equilateral triangles there. So you've got these 209 different shapes. You have to put them onto the puzzle board, okay? Completely cover the puzzle board and adhere to the lattice. You can't cross any lattice lines. Okay? He was so confident that nobody would be able to do it that he published 6 hints and offered a £1 million prize if you could do it in less than 4 years. And he deposited the money in Lloyd's of London. So the money was there to be paid out. Okay? In less than a year, 2 young mathematicians, Selby and Rizz, solved the problem. They got the $1 million prize. Unfortunately, a German, they were British, Sturton Brink, he came along 2 months late. So he gets fame, but no money. He didn't get any money. Now here's the amazing thing about this puzzle. Neither of these 2 solutions satisfied the 6 hints that Moncton gave. So assuming that Moncton actually has a solution, because he never published it, there are at most known 3 solutions. Game theorists have analyzed and studied this problem, and they have proven that there are on the order of 10 to the 95 correct solutions. How big is 10 to the 95? Well, there are fewer than 10 to the 80 atoms in the visible universe. So it is truly an astronomical number. And we've only been able to come up with 3 of them. That's not such a good trend. And the last application or recreation that I will show you, Spidrons, invented by a student of Erno Rubik, right? Rubik's Cube. One of his students, Daniel Nardelli, came up with the concept of Spidrons. And here's what you do with a Spidron. You start with an equilateral triangle. You draw in the centroid. You take 1/3 of the equilateral triangle and you fold it out. So you flip it out. So you take 1/3 of an equilateral triangle and flip it over, and then you throw away the equilateral triangle. That's what this is right here. That's where this triangle comes from. So it's 1/3 of an equilateral triangle. Then you go on to one of the shorter edges and construct an equilateral triangle, and then repeat the process. Pull out 1/3, construct, reflect, construct, reflect, construct. So you start here, that's called a semi-spidron. Take 2 of them together, you get yourself a full spidron. Now here's a homework exercise for you, because you can do this with just geometric series. The area of a semi-spidron is equal to the area of the original triangle that you started with. Okay? So in other words, you're essentially unfolding the equilateral triangle into a semi-spidron. And then you paste 2 of them together. Well, he showed that you could come up with beautiful floor tilings with spirons and semi-spidrons. But even better, he said, well, let's take and fold these along the edges so that they become 3-dimensional, and then paste them together into 3-dimensional solids. Then he discovered that they made great sound absorbers. He's patented them as sound absorbers and also as shock absorbers on industrial machinery. These polyhedra composed of spidrons. This was not cut. This was found like this in Africa. An equilateral triangular stone. We can have equilateral triangular fighting formations. This is very common, remarkably common. Many, if you're a stamp collector, you already know this, many countries publish equilateral triangular stamps. This one's from Monaco. We can have equilateral triangular danger. Now, we just had Halloween, right? So we know that equilateral triangles can be quite scary. And if you went trick-or-treating, perhaps you picked up some sweet equilateral triangles. Equilateral triangles can be sacred, or they can be secular. Now this one I really love. This is a sculpture due to John Robinson of Australia. And it's a Möbius band, which means it only has a single side. If you start here and trace your way around, you will completely circumnavigate this and come back to the start. But it's composed of equilateral triangles. If you slice through it, it's an equilateral triangle. So here's a solid object that only has one side. but yet it's pieced together out of two-dimensional objects that have three sides. That's weird. And of course, we can have funny equilateral. Now, all of the material that I've drawn on for today's talk is from a book that I recently published called Mysteries of the Equilateral Triangle, and electronic versions are free at the publisher's website. That's the URL. So if this titillates you at all, there's much, much more about the equilateral triangle out there on the website. So you can feast on that. And with that, I'll entertain any questions that you may have.
Hey, Brian,
Yes.
go back to slide number 30 if you don't mind.
What number was it?
Slide 30.
30.
Sorry.
That's easy.
There you are trying to form the smallest triangle, is that right?
Yes.
Now, the line that's going in terms of the angle, how is that angle determined, how the
Well,
slope?
there's an extra constraint, perhaps I should have
Oh.
mentioned it. You have to have one vertex on each side.
Okay.
You can't take two vertices and put it on the same side, that's cheating.
Okay.
You can put one on each side. But then you can move it around,
Mhm.
but the smallest one will be this. Any other triangle that has one vertex on each side has to have a bigger area.
Oh, okay.
That's the smallest.
Thank you.
And the only one that preserves its shape is the equilateral.
Yeah.
Any other questions? Okay, well, enjoy your